Yeah. Streaming? Is it? Are we streaming on 2 channels or 1? Just the Space Store channel? Yeah. Should be.
Okay. Welcome everybody to tonight's British Interplanetary Society lecture. I'm Robin Tucker, a fellow of the BIS and chair of the South East branch, and I'd like to start by thanking our partners in putting on this event, the Space Store, in whose Depot branch we are, and Oxford Space Systems. I'll introduce you to Juan Castillo, their business development manager later, who's going to tell us about their great technology. British Interplanetary Society is the longest established space society in the world, dating back to 1934. It works in both the technical and the popular side of space. In the technical side, it developed ideas for rockets and spacesuits before World War II, and since then has developed concepts for interstellar probes and bases on Mars. On the popular side, it runs outreach events and runs lectures and a general magazine called Spaceflight that aims to be accessible to the interested public. Just here in the Space Store, who are members of the society? Sorry, you can't see this on YouTube. Okay, we've got about half the audience is members. For those who aren't, we've got a few magazines and other publications here for you to take a look at. And obviously you can look at bis-space.com to see more and to join. So before we go on to Juan, let me introduce Stephen Ringler, who's the founder of Space Store, to tell you a bit about Space Store.
Great. Thanks a lot, Robin. Thanks, Juan, for joining us tonight. Hi, everybody. My name is Stephen Ringler, and I'm the CEO and founder of Space Store. And for those in the room, you're sitting in our proof of concept store, which we opened up about 3 years ago. And we've just recently opened up a second store in Oxford. And we're all about bringing space experience to everybody. So we like to do fun things, hands-on activities. We have virtual reality experiences. We have about 5 different experiences you can do. We have Sokol space suits, SpaceX-inspired spacesuits. We do things with schools, with Girl Guides, with scouts, for companies. And we just love people coming into our cafe here and having a chat and about space. So happy to have you here tonight. So happy to have Biz with us tonight. And Oxford Space Systems was one of our partners. So really looking forward to Juan's talk tonight. But back over to you, Robin. And thank you, everybody online, for joining, too.
Great. So over to the main event. So in my regular life, I'm a business consultant. And because I've always been interested in space, I've tried to work myself into the space industry, which being based near Harwell has been a great advantage. And so I've recently done 2 reports, one on the space sector in the Oxford to Cambridge Arc, and one on the space sector supply chain for the UK as a whole. And in both cases, this company, Oxford Space Systems, came up as one of the big successes for the UK space sector. They grew over the last several years from practically nothing, developing some really interesting technologies that are vital for satellites. I'm not going to tell you too much about them because I'm going to pass you over now to their business development manager, who is going to give you talk about how the technology works and a bit about how the company grew. We'll pass you over to Juan Castillo. I've got that right?
That's right.
Over to you, Juan.
Yeah, thank you, Robin. Thank you, Steve, for inviting me and organizing this. And thank you for all of you that made it here today. It's great to see people with interest in this topic. And also thank you to those that have joined online. So as Robin said, my name is Juan Castillo. I'm a business development manager with Oxford Space Systems. And Oxford Space Systems is located very close to where we are today. We are located in the Harwell campus. And we're a company that focuses on making deployable antennas for space. And as the title of my slide here says, the topic of today is Space Deployable Antennas. What are they and why they matter? Let me start by telling you a little bit about myself. I have a technical background. I studied electronic engineering in Universidad Simón Bolívar in Caracas, Venezuela. And I also hold a master's in digital signal processing from Queen Mary University of London and an MBA from Manchester Business School. Before working in business development, I held a number of technical roles. I designed a few electronic boards for the telecommunications, aerospace and defense. I did firmware for FPGAs. These are programmable devices. And I also work as a systems engineer, both in the Pacific Northwest and here in England in a number of companies, those that you see on the screen. I am not an antenna engineer myself, but throughout my career, I have worked with several very good RF engineers that have taught me the basics to understand what's happening. And that, by the way, reminds me, is there anyone in the audience that is an antenna engineer? Okay. It seems like no one is an antenna engineer, which is great news because you will not be able to tell if I make a big mistake. So my objective for today is to give you an intuitive understanding of how antennas behave. And I also want to show you why deployable antennas are important in space. And finally, I want to show you some of our game-changing designs for deployable antennas. One of my earliest memories of antennas it goes back to my childhood. This building that you see here is where my grandmother used to live in Boston, Massachusetts. It's one of those beautiful, typical New England red brick buildings. And as a kid, I would go and spend time with her during summertime, and sometimes I wanted to watch some TV. There was a problem. She lived in the basement flat of the building. And the reception was terrible. Really, really bad. Back then, as a kid, I didn't know anything about engineering, RF, antennas, or radio waves. But I had this concept that there was some signal in the air that somehow had to get into the TV so I could see a picture on screen. And I knew that those walls were getting in the way. So what I did is what most kids would do. I took my grandma's TV that used to look like this one here. And you may now be thinking about my age. And I took the antennas. They were one of these antennas that you could, stretch, move around, make it longer, make it shorter. And I would tinker with them until I would get some sort of signal. And in a good day, if I got lucky, I would get my cartoon, watch it, and be happy. But why tinkering with antenna would make any difference? Why having a longer or shorter antenna pointed in a certain direction would affect the picture I had on the TV? I would have to wait many years for that answer. But it has to do with antenna properties. And the shape of the antenna, length, affect a lot of different things that are closely interrelated. Now, if you go to a university course, chances are they will start explaining this to you with a few complex electromagnetic equations. I won't do that today. I will do something that is much simpler. I would explain it the way that Dr. Cao Wan, our RF, the head of RF at Oxford Space Systems, explained it to me. He said, I want to imagine a party balloon and think of that balloon as the distribution of RF energy. And RF stands for radio frequency. Now, in a theoretical sense, you can imagine that in the middle of that balloon, there is an antenna that is a single dot. There is shaping this energy in equal ways or in all directions. So it's a bit like a sphere. And this theoretical antenna, we call it an isotropic antenna. The shape of the balloon, we call it the RF pattern. And this theoretical antenna is important because all other antennas are compared against this one. And I will explain that in a moment. One important parameter of antennas is gain. So how much energy they can push towards one side. And the gain of antennas is, again, measured against this one. So in this case, we say the gain is 0 because we're comparing the antenna to itself, so there's no change. One practical approximation of an isotropic antenna is an omnidirectional antenna. And this can be achieved using a monopole, which is a single wire, or a clever arrangement of dipoles. Even though they don't have gain, we call it gain 0, they're still very useful for satellites, especially during the in-orbit commissioning phase. When you first launch a satellite and it leaves the rocket, it's tumbling, it's not pointing to any particular direction, but you want to be able to still send signals to it, commands, and get telemetry back until you're able to stabilize it. And an omnidirectional antenna is really good for that because it's able to pick signals in pretty much every direction. Now, by changing the shape of the antenna and the architecture, you can change this pattern. You can, for example, squeeze the balloon and get, in this case, what we call a directional pattern. So most of the energy now is pointing upwards. What that means is that compared to the isotropic antenna that we had before, we now have gain in that direction that is more than 0. And this is very useful because when you direct the energy to a certain place, you can simplify the circuitry in your satellite. You can reduce the amount of power that you use. Therefore, you don't need that many solar panels, and you can reduce the size of your power amplifiers and many other things. So directional antennas are very useful. And one thing that creates a directional antenna, for example, is this helical that we have here. It would create a pattern similar to this one. Now, you could still squeeze the balloon even further to get more gain. And you could do that with a parabolic dish reflector. So the circle at the bottom, the gray circle, is a dish. And you can see the gain is much higher. Now, nothing in life comes for free. There's always a trade-off, and all engineers know that. And one of the trade-offs in this case is that in order to get more gain, you sacrifice coverage. You can see the red bit is higher than on the helical case, but the coverage around it is not as great. You can also do other things with the balloon, again, by changing the architecture. You can flatten the balloon to get yet another pattern. And each of these patterns have their uses. In this case, you still see gain in some directions compared to the isotropic one, so more gain on the side. And an antenna that would do that is an elongated helical antenna. Now, you might be wondering, why do I want this type of pattern, which looks like this? The answer is, when you are looking at a satellite, if it's directly above you, the distance between you and the satellite is much shorter than if it is towards the horizon. But if you wanted your satellite to provide equal power on all the regions, you want an antenna that has a lot of gain on the side and not as much gain on the center. And that is what this pattern does. It's called isoflux. And let me put that into context. So I will start with the gain. So we have planet Earth, and then we have our high gain reflector antenna. As you can see, it can produce a lot of gain, but covers a very small area on the ground. Or you could have your isoflux pattern that maybe doesn't have as much gain, but it covers a much wider area. Now, some things to remember about antennas. 2 points, essentially. One that I haven't mentioned, but it's important to know, is that the antenna size is inversely related to frequency. So here I have a picture of a radio wave. It goes from low frequency, long wavelength, to high frequency, short wavelength. And intuitively, you may think that for long wavelength, you need a larger antenna than for a shorter wavelength. And that, more or less, is a rule of thumb that you can use. So if you see a very large antenna, it could be because it's operating at low frequencies. Another important thing related to size is that a large antenna equates to high gain. And high gain translates in turn to high performance for the satellite missions. And this last point is a very important point for my company, Oxford Space Systems, because that is the reason that drives most of the designs that we make. I'll talk about that a little bit later, but before then, I want to talk about some of the antenna applications when it comes to space. The first one is communications. Most of you are familiar one way or another with this one. Normally you get an antenna that is used to transmit audio or video or just data. It could be from a satellite to the ground or between satellites as well. And in this case, you want a high gain antenna because high gain equates to a higher data rate. Another interesting application is Internet of Things from space. We work with a company called Lacuna Space. They produce this transceiver that you see on the image here. It's a LoRa standard transceiver for Internet of Things, and they attach this to pretty much any type of asset that you can think of. You can, for example, have it in the field, measuring the level, the temperature or the moisture on the ground. You could attach it to animals. They have a use case where they attach this to elephants, and using our antenna in their spacecraft from space, you can pick up the signals of all these transceivers. And in the case of animals and elephants, you can see, their migration patterns, and you can gather the data from all the devices that you have on the ground. Another good application of antennas in space is the collection of AIS signals. AIS stands for Automatic Identification System, and it is a system, a transceiver that ships beyond certain size need to have by law. There will be all sorts of interesting information in these signals, like the name of the ship, what cargo they have, where they're going. By having satellites with antennas that can pick up this signal, you can start tracking all these ships. You can measure things like the level of commerce in certain area, or what type of goods are passing through. And finally, I want to talk about one of my favorite applications, which is synthetic aperture radar, or SAR. I like this one because it's almost like magic to me. Everyone has a phone with a camera, and you can take pictures with it. But this is a technique that uses an antenna to produce an image, a picture, that looks something like that. And you have satellites with cameras that take incredible, beautiful pictures. but they have a limitation. And the limitation of a camera has to do with the fact that it works on the visible part of the electromagnetic spectrum. And if you have a cloud in the middle, you won't be able to see anything but the cloud. Or if you're passing over an area during nighttime, you won't see much either because there's not much light. However, with SAR technology, you use radio waves to send them to the ground. They go through the clouds, they bounce off the ground, and they go back to the antenna, and then to the SAR payload. And after some clever signal processing, you have your image. You can create these images regardless of weather or light conditions. Doesn't matter if you have clouds, doesn't matter if it's nighttime, you can still produce these images. And they have all sorts of interesting applications. They have object recognition using artificial intelligence, or you can detect changes, floods, and these days, for security purposes, the governments also like to use it to monitor activities on the ground. We do have antennas in this area, which I will talk about later. But before I get into that, I want to answer the question, why deployable antennas are important in space. And it has to do with several factors, but one that is very important is a trend that has been happening in the last decade or two. And it has to do with advancement in semiconductors. Thanks to the PC industry and the mobile phone industry, chips have been getting smaller and smaller and more powerful. That has driven the electronics in the satellites and a lot of the components to be smaller. That makes them cheaper. And also because they're smaller, it is easier to launch them. So now this is not just the domain of governments and agencies like NASA and the European Space Agency, but also commercial companies are entering the market to offer different services. So on the left, we have a traditional satellite. That's a picture of a Sentinel satellite, very large. And they still have their place and a lot of applications. And on the right, we have a CubeSat that are becoming or are already quite popular. And a lot of our customers will be in this area or somewhere in between these two CubeSats or microsatellites, which are satellites usually below 200 kilograms. Now, how do you reconcile the need for having a small spacecraft with the fact that you still need high performance in orbit? And high performance, once you are in space, means a large antenna. And the answer to that is you have to use a deployable antenna. So deployable antenna allows you to have a small satellite, a small box, where you put it inside the rocket, and you could perhaps put several satellites in the rocket because you don't need that much space. And once you launch them and you lift the rocket, you can still deploy your antenna and have a large antenna to give you the high performance you need for the mission. And at this point, I want to talk about some of our game-changing designs of deployable antennas that are helping our customer achieve high performance on orbit. This is an overview of our antennas, and I will go into detail on each of these. So on the left, we have a Yagi antenna, which is used for AIS maritime applications. So you may remember AIS is the signal that ships transmit, and you use them to track the ships. We have one of these, our customers have one of these going up at the end of the year, and we have two more going up next year. Then we have helical antennas for Internet of Things. These are antennas that operate around 900 megahertz, and we have 5 of these flying already. They have deployed correctly, and they're working beautifully well. And The two in the middle, the wrap rib and the offset reflector, they're large antennas. They're not for CubeSats. They're for bigger satellites of 50 to 150 kilograms. And they are for SAR applications. The last application I mentioned where you can create an image from an antenna. And they vary in diameter, but they're large. We're talking 3, 4, 5, 6 meters in diameter. And if you were to go and visit our company today, you would see two of these in the clean room. It's quite impressive to see them in real life. And finally, I have the hinge rib, which is a sub-meter antenna, operates in K-band, very high gain, and is ideal for high-speed applications. So let me show you how they work, how they deploy, so you get an idea of how the technology is designed. So the first one is this helical IoT antenna. I'll play a video. So we have 5 line in CubeSats. As I said, they're for IoT, 900 megahertz, high gain. The antenna has 3 radiating elements which allow it to not use a ground plane. They stow in about 1 U, which is 10 by 10 by 10 centimeters. And then a thermal knife releases the lead, and the antenna deploys using its own strain energy. It's a very simple but reliable mechanism. Right. So now I want to show you our Yagi antenna. This is a little bit like my grandma's TV aerial. It operates in a similar frequency as well, perhaps a bit lower. Also is compatible with CubeSats. It's good for AIS and VDES, which is another standard, but a little bit more advanced for vessel communications. It's high gain, has 3 elements. This one uses a little bit more space, 1 U, which is 10 by 10 by 10. And again, a thermal knife activates the deployment mechanism, and then its own strain energy makes it deploy. As I said, we have one of these going up at the end of the year with one of our customers, and 2 more in 2023. Now I want to show you some of the large antennas. This is the wrap rib antenna for SAR applications on X-band. It uses metal mesh, so it's the reflective surface, and carbon composite ribs. It produces a very high beam that allows you to have a high resolution image. So when it stows, it's very compact. And the first thing that deploys is the main reflector. The ribs deploy radially. And then you have 4 booms in the middle that will deploy the secondary reflector. And as you can see, compared to the satellite, then you get quite a large structure on orbit. The other antenna that I want to show you that is on our SAR category is our offset reflector. This one operates at C-band, so slightly different frequency. So depending on the frequency, you get different attributes on your SAR image. And this one doesn't use metal mesh, it uses a carbon composite membrane that allows you to have a more accurate shape. And the better the shape, the better the RF performance. You could have multiple beams on this one. And it stows on the side like that. And then you get an arm that deploys what we call the ring deployable structure. And then the ring deployable structure opens and you get your large offset reflector for SAR applications. The last one I want to show you is our hinge rib. This one is, again, compatible with CubeSats. It's used for either inter-satellite links or satellite-to-ground links. It operates in Ka band, Ku and Ka, and it's very high gain. We are completing the qualification of the antenna right now, and it's dosing 2U, so it can go into a 6U CubeSat. And next year, we're planning an IOD, an in-orbit demonstration mission for this antenna. So I hope this has given you a basic understanding of how antennas behave, why it is important to have a deployable antenna in the space industry, and also giving you a flavor of some of our technology. Before I finish today's talk, I want to mention something else, and that is you have seen what we can do. We have all the right building blocks, and we're starting to get space heritage to achieve our goal of becoming the global leader in deployable antennas for space. For this, we have a number of important skills in the company. We have a team of RF engineers, because every single antenna starts with RF design, looking at what is the RF pattern we need to achieve, the gain, and other parameters. We also have a large team of mechanical engineers to figure out what's the best way to stow the antenna, to come up with the right architecture, to come up with a design that can survive the launch vibration. And we have people that understand materials, because space is a harsh environment. You need to survive vacuum, temperature cycles, and other difficult situations. If you are interested in our antennas, of course, please do get in touch. But equally, if, like me, you had an interest in antennas when you were a kid, perhaps playing at your grandma's home or on your own, do reach out, because we are growing. We're 60 people at the moment. We have opening positions, which you can see in our website, and we would love to hear from you. So I do hope that some of you go and visit and see if there is a fit for your skills. With that, I want to thank you for your time and open the floor to questions.
You mentioned the helical antennas. Do they produce circular polarization, or what do you get?
They do, yes. So a helical antenna would naturally produce circular polarization. Yeah.
So that you can produce circular polarization by vertical and horizontal, feeding them with phase current.
Yes, as well, you can do that. But our helicals would naturally give you a right-hand circular polarization or left-hand, depending on what the design is trying to achieve.
So presumably, to receive a circularly polarized signal, you need another helical antenna on the ground in the same. The helix in the same sort of orientation, going around the same way. You
need to align the polarizations. You're probably right, but I'm not 100% sure right now. So I don't. Yes, yeah, but you do need to align them so you can receive. Yeah. Yeah. Any other questions here in the audience?
Yeah, I think.
I was just wondering how, so like, I don't know what orbit, like how susceptible they might be very in small parts of these antennas might be to like damage from meteorites, or also like, I don't know, this is like the future thing, but how likely they might be damaged when like there's an increase in like these like satellite things that are in like networks, and so like there's increased spatial. I'm wondering like how much you'd be worried about that affecting these like they seem like quite small parts and quite thin.
Yeah. So the question was, how susceptible are our antennas to a foreign object hitting them, like a micro meteorite or the, yeah. Yeah, so they are susceptible. Yeah, they are, because the antennas are designed to be rigid enough, stiff enough to meet the mission requirements, but we don't over-engineer, because you could end up with something that is very heavy as well. Yeah. Having said that, some of our IP in metal mesh. So, for example, the antenna that we have on screen right now uses metal mesh. That is that material that you see between the ribs. So we knit that. We have a knitting machine in the company that would produce that using tungsten, gold-plated tungsten. And we have developed IP on the knitting pattern to, number one, optimize the RF, but number two, be resilient to things like micrometeorite. So if a micrometeorite were to go through this metal mesh, it would of course make a hole, but the hole wouldn't propagate. So it would degrade in an elegant way, let's say.
You go
A question about, I'm just interested in the mechanical design side of things. Just wondered, are all of your designs using, do you always use strain energy as the main way to deploy all of these things? Because you said you use a thermal plate. So I'm guessing you tend to avoid using something like a stepmotor or some kind of physical mechanism. You'd rather you go for something simpler that's just going to deploy it to you.
Yeah, we use both. So in the helical, the little helical antenna, which is about 30 centimeters, and the Yagi, which is a bit longer but still small, we use strain energy. For some of the larger antennas, like the 3, 5, 4, 5, 6 meters, we would use motors to deploy several areas. And this one here, it would use DC motors.
And by strain energy, you essentially mean just a spring, the springiness of
Yeah.
the
So
material.
it's the energy contained within the material when you fold it. The material itself will want to come back to its natural shape.
And can the mechanisms be driven backwards? Can you track the antenna?
At the moment, the designs that I show you are one-shot deployment.
This question. Is there any limitations on the orbits that can be up to geostationary orbits, or is there any limitations on that?
Yeah. Most of so the question was, are there any limitation on the type of orbit and altitude? Most of our antennas are designed for LEO, low Earth orbit, because that's where our customers focus on. Having said that, we do have developments that go beyond to GEO and even cislunar orbit. A lot of the work comes down to analysis and test to bring confidence. Sometimes a design is adequate. A LEO design may not have to change that much, but you do need to prove that it can survive the new conditions. And sometimes you do need to do something different to survive that environment.
Is there a question over here?
When you download data from the spacecraft to the ground station, certainly the antenna has to point at the ground station. As the spacecraft moves, are you able to move the antenna remotely to point at the ground station, or does the whole satellite move?
Yeah, so normally our customers would deal with that problem, but there are two typical solutions to that. You either use a gimbal, which is a mechanical device that allows you to move the antenna, or you move the spacecraft itself to point in the right direction.
So you can do either?
Yes. Yeah, it comes down to mission requirements, the budget you have, etc., etc.
Were there questions online?
We do. Would you like to read that, or would you like me to?
Okay, so gosh, deployable antennas. Yes, you've got albedo effects, so I presume that's affecting. So there are dark sky concerns. Are those better or worse with deployable antennas, and do you make that a consideration when you're designing antennas? So this is the fact you're looking up at satellites and worry about whether the sky remains dark.
As far as I know, and I'm not an expert in the subject, deployable antenna should not make that much difference. I suppose you're talking about the reflectivity of the antenna. Yeah. Yes. So I wouldn't be able to comment much, but I would say that the difference between it comes down to the materials and perhaps the coatings that you use more than the deployability in itself.
Yes, I wonder if a mesh one might have a lower albedo than a solid material, just because most of the light goes through.
Well, there are translucent. Yeah, so in that sense.
Okay, and then someone called Tim has got a question about the Artemis missions are coming up, and people are obviously heading for the Moon or Mars. Are there scope for deployable antennas on interplanetary missions?
Yes, of course.
Of course.
Yes. The answer.
Listen, you'll be waiting for it.
Yeah, no. There is scope. At the moment, I'm not allowed to disclose much, but I would say by the end of the year, we should be able to make an announcement with one of our customers in that area.
Okay. So what I do know, and I don't expect you to comment on that, is that I believe Surrey Space Systems are involved in a European Space Agency project to provide communications for moon missions. That's public knowledge. But of course, I don't expect you to comment on whether you're involved in anything like that. Okay, and a question about antenna footprint from Keith. Antenna footprint for ground receiving stations. What angle of incidence to the antenna is required to receive a data link? It's a bit of a slightly technical question.
Yes. So I think there are a few things missing from that question, but what I would say in general, and I don't know if this helps. Keith, you said was the question, is that, as I said, that there's a trade-off between gain and area coverage. And if you have a very high gain antenna for a high-speed data link, what that also means is that you need to be very accurate when you point so that your beam reaches your ground station. And if you have less gain, you may have more coverage. So you may not need to be as strict when it comes to the angle in terms of receiving the signal.
Right. And does the atmosphere affect it at all, or can you go right down to the horizon effectively for satellite communication?
I wouldn't be able to comment.
No, okay.
I think, it's very,
You didn't claim to be an RF engineer, so.
No, but I suspect, there things like frequency certainly play a role.
Yes.
And other parameters as well.
Okay, here's a different type of question completely from Alejandro. Does Oxford Space Systems offer summer internships?
We do have apprentices.
Mm-hmm.
And the best thing would be to go to a website or to send an email to explore at oxford.space, and then we can talk to HR.
Yeah. And I think there's that goes for several of the companies on the Harwell campus. It's obviously space is obviously a very rapidly growing industry and needs to build up a skill base. So there's a lot of opportunity in there, and lots of the larger companies are investing in people and bringing them on board and providing training necessarily on the job. So I have a question. There's obviously a lot of clever design in these components, but obviously, but I think a lot of clever materials, and you've talked about the materials that help the antennas spring out of the satellites. Is that usually carbon fibers, or are there metal springs as well? And how much goes into the materials as opposed to the design of the components?
Okay, in two parts. We use a variety of materials. Yeah, we use carbon composites. We use glass fiber. We use metal, as in spring metals, and the selection of the material goes hand in hand with the design and what you're trying to achieve. So the answer about what material you use, it depends on what you're trying to meet. But we do use, yes, a plethora of different materials, and some of those will give you better stiffness, some others will behave better over temperature, and some others would be better in terms of RF, in the sense that they may not interfere with the RF.
Right. And any other questions from the floor? Here? Yeah. There and then there.
Yes, so previously you were talking about how the antennas use gold tungsten coating on top. And so I was wondering, as you continue to increase the size of the antennas, obviously this is going to, with the increase in size, it's going to become more susceptible to space debris. And I was wondering if you were potentially looking at a self-healing metallic composite coating for the antennas, instead of just looking at a weave.
Yeah.
If that was it.
So the stage where we are at the moment is we are trying to produce high-performing antennas and gain space heritage. When it comes to the metal mesh, all the activity that has happened in the last couple of years are related to establishing the capability of producing that, because it's not as simple as you might think. You'll be surprised the amount of IP and effort that goes into producing that. Previously, we were buying that from the US, but it's difficult because in the US you have something called ITAR, which is, I think it stands for International Treaty or Arms Regulations or something like that. But what it means is that you need a license to get things out of the US, even if it's a simple component. And that can be a very cumbersome and long process. And in Europe, there are not that many suppliers of metal mesh for space antennas either. So we're trying to get that right first. And we do have an R&D department that is working on, what comes next. I would say that that's probably in the future. I don't know for sure, but right now, self-healing is not in the immediate future.
Great. And
so obviously I think one of the USPs is the miniaturization that we've seen over the last 5 to 10 years. Obviously having a deployable antenna on a CubeSat's a lot better than trying to put something on there that deploys when it's up, that doesn't deploy when it's up there. But have you looked at the risks of your deployment mechanisms failing with your strain-based deployment systems? Is there any risk of any space debris being put in low Earth orbit? I know it will probably burn up in 10 to 50 years, I don't know what the range is. But is there any risk of any space debris being produced from your deployment mechanisms?
Well, two things. The first is there's no such a thing as no risk, especially when it comes to space. Yeah. But we do follow a very robust design, manufacturing, and test process. So before we produced this antenna, we would have produced a breadboard to test the basic functionality, an engineering model to take it a step further. Then we would qualify it, meaning, for those not familiar with the term, it just means you take the antenna through vibration to simulate the launch. You take the antenna, you put it in a vacuum chamber, a chamber that sucks the air, and then you thermally cycle that. Sometimes you would subject the antenna to shock as well, to simulate the coupling from the rocket. And that at each of these steps, different risks are being mitigated. So by the time you have an antenna that is ready to fly, your level of confidence is very high. The other thing I would say is that to date, we have 8 different structures in space, deployable structures. 5 of those are antennas, and we have 100% success rate. The designs themselves, when they deploy, we don't release materials that stay floating. So that's what I would say, but nothing is 100% risk-free.
I mean, you've just done brilliantly in answering a question that Keith has asked, which is, does the deployment of the antenna release any materials or debris? So the answer to that is no.
No. It stays, yes.
I'm sorry, one more question. Of
Sure.
course. New deployment mechanisms, I presume, that add some additional shock or vibrations to the spacecraft payload, whatever. Do you have to work with the customer to model what
Yes.
that impact is on the spacecraft so they can come up with the tests for that?
Yes, we do work with
Yeah.
customers, and that's a question that comes up.
Yeah.
Another question that comes up as well, somewhat related, is the rigidity of the antenna, that it doesn't couple with their attitude control system. So a lot of these antennas, so for example, the 5 that are flying, the mass is very low, and even though they fly in CubeSats that are very small, when they deploy, you could barely notice it in the telemetry. Actually, you see a little glitch and then it goes away. But yeah, it's something that we look at along with a lot of other parameters like the thermals, how the heat propagates, with the spacecraft itself interfere with the radiation pattern. There are always a lot of questions that we need to answer so that our customers feel confident that they can use our antennas.
As you were asking the question and you were asking it, I was just thinking back to the James Webb Space Telescope and the 400 explosive and other deployments that had to happen all perfectly, and half of them all at exactly the same time. Otherwise, $10 billion worth of space telescope development would be gone. So we have one. I've got one more question here. Which Space Store team have answered online, which is what was that picture up there to the left of the monitor, which is northern Greenland. And you can buy a coffee if you like online at Space Store, or indeed here in the shop here at Decox or Oxford. Fantastic. Well done for answering that.
That wasn't a plan.
Plus many other great items. Okay, any other questions? Or should we wrap there? Great. So thank you very much.
Thank you for having me, Robin. Thank you.
Thank you to our audience here in Decox. Thank you for those of you joining us online. I hope you enjoyed this British Interplanetary Society talk, and being here virtually and in reality in the Space Centre. I'm just looking opposite at the kind of experience zone here, and there's a sign up saying there's a toddler group every fortnight on a Tuesday. I'm thinking that the toddlers who come to there 20, maybe 25 years' time, they'll be going to work at Oxford Space Systems, which by then will be, what, £1 billion company making antennas for the Mars colonies.
Let's hope so. Sounds like a plan, yes.
Thank you very much again, Juan, and thank you to the Space Store team who's been looking after us tonight. And
Thank
good night
you.
to everyone
Thanks.
on YouTube.